Hello. This is going to be the third and the last session of modern anomaly and novelty detection. Uh, Today, we're going to talk about mainly about the deep learning section of the way that you can find outlier in your data. As you may remember, the first day we will talk about more of a statistical and distance-based models. The second day was mainly about machine learning model like one-stream, observation forest, and clustering. Today we're going to talk about how we can use and take advantage of all those new concepts which we are hearing in last, I would say, decade. Which is basically all those type of deep learning models that you can use: RNN, CNN, autoencoder, variational autoencoder, GANs, all those things. So the thing is, we can use all of those models for different tasks. But the thing is, as I have said before, the reason that I didn't just talk about the deep learning model was because depends on your task and data. Your data, you should use different model. Maybe if you have like a small set of data, or your outlier is not that hard to catch, maybe just a statistical model will be fine. Or maybe just using isolation first, which just trying to isolate a node, should be enough for your data, or just applying one stream. So the thing I'm saying is, like, depends on your data. You should choose the type of the model that you want to use. It shouldn't be always a fancy, let's say, GANs-based model just because we can. Because sometimes it's like a overkilling the task. It's like using super complex model when you could just capture those outlier, or I don't know, if you're dealing with, I don't know, outlier or novelty, or if based on your task, you might not need to use deep learning. But whenever you have a complex data, when you need to capture or extract some hierarchical information, whenever you're dealing with some maybe a sequential data or image, when you have, like, when the number of dimension is super high, then for sure you have to use deep learning. Then that's the time that you're switching to deep learning models. And then here we're going to talk about different types of deep learning models. Uh, for sure, not all of them, but we want to review some of them. And during the workshop, we'll try to have some hands-on experience with some of these models to see how can we use them and when they are useful, and how can we actually take advantage of all the things that we can given all these models. So today I will talk briefly about self-supervised learning and some sequential models, autoencoders, and generative models, which will be basically variational autoencoder, adversarial autoencoder, and GANs. And we'll see how can we use them. So first thing first, what is self-supervised? Self-supervised is basically when you don't have any label, which for us would be basically everything, because we are in semi-supervised and unsupervised type of anomaly detection and outlier detection. We don't have any label. So basically, most of these tasks that all these models that we are talking about will be kind of in the area of self-supervised learning. Is like when you don't have any label, but you're using the data to be your label. So there are different ways that you can do that. So sometimes you can just use a part of it. You can just use a part of your data and make it to be your own task and try to predict it. So basically, the thing you should do is, like, find a task. It can be anything. It can be, as I said, part of your data, or it can be something which you will say that, given that, I don't know, image, I should be able to find a part of it. I should be able to, let's say, if you have like a colored image, you want to be able to predict the grayscale of it. So it means you can be creative. You can generate any task, but you're making the task or label based on your data. So you don't need any supervision here. So the supervision will be with just maybe a different alignment of your image, or maybe if you have a sentence or character, maybe it will be just what will happen in the next sentence or something like that. You're using the data itself to be able to make a task. So you have to find the task, and then train a model, and then monitor how well it will do on the task. If you have a model which is performing very good, then you can have it as your base model. That from that moment you can say, if I can't predict anything good enough, then maybe my input data was not from the same distribution of my training data, and then maybe you can flag it as an outlier. For one of the things that which will be useful here is like all those time series data, which because you have a series of input, all of them have are sequential, so you can say that maybe the next one is a prediction of the one that you will have right now. Or if you have some concept in your data, let's say you're dealing with a sequence of insurance claim, maybe you can say the summation of all the money that you will claim the next year can be the prediction for the current claim, something like that. And if you choose a good task, one that is hard enough, the model will learn some high-level concept about the training data. It will find some interesting correlation, interaction, and all those things, lots of pattern from your data, and become confident in some prediction. And then things, all these models and these things will likely break for new observation that are not from that data or is super difficult. So then that would be your task. And even autoencoder is we can say autoencoder is a self-supervised one, which instead of predicting a part of your data or some task that you're defining, you're actually predicting everything. So so all those autoencoder model is a subset of a self-supervised technique. So that's it. So this technique is actually getting used in lots of places, and it means converting your unsupervised prediction to a supervised one by just defining a new task. Remember when I shuffled the data and made it to be kind of like a supervised one? Whenever you can do something like that, a trick like that, it will make everything easier for the model. Because right now, for supervised part of the machine learning, we get to the point that we have lots of techniques, lots of models, lots of metrics that we can measure, we can tune, and we can make it better. But whenever we're talking about unsupervised or even reinforcement learning, there are lots of problems, those are, I would say, a bit harder to solve. So that's why if you can in any ways convert it to supervised, then life would be a lot easier if you can actually find a task that will learn all the pattern in your data. So that I would say is one of the most important lesson that you can get from this workshop is self-supervised model maybe will be the future, because we don't have any labeled data for all those tasks that we can have. And if you can use part of the data, then you can train anything you want. And even for our task here, which is anomaly detection, we're just saying that we don't care about the task as far as the model is working good. You can just use it as a base one. And even for the next step, why should you have just one task? You can have multiple tasks. Like let's say for insurance claim, you can predict the length of the stay of the claim. You can predict the cost. You can predict different maybe the diagnosis code, procedure code, all those things, and then you can combine them and say, okay, given a new claim, give me the accuracy for all these tasks. And then you can have like a threshold that if you are good at maybe let's say half of them, maybe normal. If you're less than something, you're not. So you're adding an ensemble technique to it as well. So then you will get to the point that you're talking about multitask learning, that which will kind of help you to have multiple tasks, join them, and be able to use it for your own task. So the first thing that I want to talk about, which will be like kind of like a subset of self-supervised learning, would be auto-regressive models. As you remember, for all those generative models, the thing that you were trying to do was learning the distribution of the data itself, learning the p of x. What is the probability of x? What is the likelihood of x? And if you can learn that, from that moment you can say, okay, the likelihood of that sample is super low, so maybe that sample is not from my data set, so maybe that's outlier. So the way that here we're dealing with is there we can learn the probability distribution of peaks by kind of breaking it into multiple pieces. That pieces can, if you're dealing with the one sample, it can be like an image or any non-sequential data. You can treat each dimension as x1, x2, x3, something like that. So you can have a list of all the dimensions, and then just by using the chain rule probability, you can factorize that joint distribution over this n dimension. So then from that moment you can say, okay, the probability of x is equal to probability of x1 and times probability of x2 given one, and etc. And then you can say, if I can compute all these things and multiply them, I should be able to learn the distribution of it. And using that simple technique, there are lots of models that have been generated. Like for text, all those language modeling, which means given a word, you want to predict the next one. Given these two words, you want to predict the third one. It basically, then you can multiply the prediction that you got, and then you can say that's the probability of the sentence. And once you learn a model here, then once you have a new sentence, which all the wording is wrong, then you will have a lower probability per word. Once you multiply them, you will have a lower one. And given a threshold that you can define, you can say, okay, that sentence is outlier. They're using the same technique for image. So you have like a two-dimensional pixel. The thing that you need here is just ordering. It can be any random ordering. You can start from the top. You can say prediction of each pixel will be based on the previous one and the previous one. So you can kind of use again the RNN for predicting the next pixel in the image, which they call pixel RNN, or you can even use CNN, like the image here, that you're just using a part of the image and you're predicting the next one is a pixel CNN. They have used it for audio and for text and for different things, and the whole idea is using the chain rule of probability and to be able to learn the distribution or px of your data, which is a great technique. But and the thing is, if you have enough data that you can do that, then you will be able to learn the probability of your data, and then you will have, then from that moment you will have a generative model, and so you will have a good author detection model.